Hello, welcome back to part 2 of group cohomology, group and Galois homology. So just a recap, remember what we were trying to do was start from a sequence, a short exact sequence of G modules, and then look at the exact sequence that you get when you do G invariants. It turns out that that is not always exact on the right, and we're trying to fix that, find some G module that would make that exact. We've done that, and this theorem says that the definitions that we made for H0 and H1, these cohomology groups, do what we want. Do what we want because H0 is actually just the G invariance. So this, the beginning of this sequence is G invariance. And it just continues through delta into the H1s. So it gives you some other modules that make this a long exact sequence in cohomology. And it keeps going into H2 and H3 and so on. But the goal here, or the good thing, is that sometimes one of these will be 0. For example, H1 might be 0 here, in which case the sequence of G invariants is actually exact, or this might be 0, or this might be 0. And when there is a 0, we can actually cut the sequence and make it an exact sequence from 0 to 0, and it's just a finite exact sequence. Not a short exact sequence, but an exact sequence nonetheless. Okay, so this is how we define delta. So let me do some, first of all, some remarks about this definition. So the definition again is that for an n in the G invariance of n, we pick an m in M such that beta of m is n. Beta was surjective, so I can pick an m that does that. And we define phi that goes from G into P by this definition. And then it turns out that phi is a cocycle, and that's how we define that cocycle. So some remarks are necessary. First of all, in the definition of delta, the image of alpha is identified again with P. This is identified with P as a subgroup of as a submodule of M. Okay, and then it is also identified with P being the image of alpha is the kernel of beta, so this is the kernel of beta, and now we can actually prove that delta is well defined. So remember that delta is defined or by this cocycle, what we claim is a cocycle from G to P, such that phi of sigma is sigma m minus m, where beta of m is n. Okay, for an n in ng, for n in ng. So what we want to prove actually is that this is not clearly in P. So is this so? Is it in P? Let's prove that it is indeed in P because it is in the kernel of beta. So let's see that it's in the kernel of beta. So beta on sigma m minus m, what is that? That is beta on sigma m minus beta acting on m, or the image of beta. And this is sigma beta is a G module homomorphism, so sigma can come out minus beta of m. Beta of m is n, so this is sigma of n minus n, and n is in the G invariance, so this is 0. So, so yes, phi of sigma is always in the kernel of beta, which, as I said, is identified with P inside of M. And therefore, yes, you get a map from G into P, okay? And it's not hard to prove that this is a cocycle. What is interesting is that phi is not a coboundary. It's not necessarily a coboundary, even though you see how it's defined. It is always defined. It is always sigma of m minus m, like the coboundaries are. But to be a coboundary from G to P, it would have to be that M is in P, but M is not in P, M is in M. It's not necessarily in P. Okay, so because M in the definition is in M, but not necessarily in P. Okay. Phi is actually a cocycle, is a one cocycle. And the proof is just as in the definition of the coboundaries, actually. So I will leave that to you. The fact that the coboundaries are always in the cocycles. Again, this is not a coboundary, but it is still a cocycle for the same reasons. You can just sigma tau m, just subtract and add and subtract sigma acting on m, and you get that that's a cocycle. Last, the proof of the theorem. I'm not going to prove it, but the proof of the theorem is diagram chasing. So it's it's kind of tedious, but it's not difficult. So you can try it. So we will skip it. Okay, so let's do some applications of the theorem instead. Remember that we had actually talked about Hilbert's theorem 90. So I'm going to prove this using the other parts of Hilbert's theorem 90, but we're going to use this. We're going to use the theorem to prove that. So here is one application of the theorem on the long exact sequence in cohomology is that H1 of the Galois group acting on mth roots of unity, this is actually isomorphic to k cross modulo k cross to the mth power. This is if the characteristic of k is 0 or the characteristic of k does not divide m. Okay, so let's start from one short exact sequence and then take homology groups. So we can start from the sequence that goes from k cross, actually k cross bar to k cross bar, that takes, that's just mth powers. The kernel of that is precisely the mth roots of unity of k. And this is in k bar, so the nth powers are surjective. So this is a short exact sequence of cohomology of Galois groups. So this is an exact short exact sequence of Galois modules. So we can take cohomology groups and see what happens. When I do cohomology, I'm going to get 1 goes to, I don't know that the mth roots of unity are in k. So when I do G invariance, will be whatever mth roots of unity are in k. So that is k cross intersect mth roots of unity. The Galois invariance H naught of k cross bar will be k cross by Galois theory. I get the map induced here is still taking mth powers, and the invariance of k bar cross is k cross, and then it keeps going into the H1s. It will go into H1 of the Galois group of k bar over k acting on mth roots of unity. That's what we want to compute. And it will go into the H1 of the Galois group of k bar cross, and it will keep going, okay? But we're not going to need to go any farther because by Hilbert's theorem 90, this is 0. Okay, so this is by Hilbert 90. That is 0. And we know that it's exact, the map, this is exact, so I know that the image in here is the kernel of this one. The image of the mth power map is the mth root, the mth powers. So the image here is the kernel here, then that I can do an isomorphism then that K cross, so this map induces the following is K cross modulo its kernel, which is the image of the previous map, will be isomorphic to H1 because the next item here is a 0. Okay, so let me just say that because now I've mod out by the kernel, what I do get is that this is injective because I modded out by the kernel, and on the other hand, by Hilbert's theorem 90, the next Galois module is 0 there. So this map has to be an isomorphism in the middle. Okay, let's write it like this. So now this has to be injective and surjective, and therefore this is an isomorphism, which is what we wanted to prove. Okay, we've seen that in one of the examples in the previous lecture with K being R. So remember that we saw that the H1 of the Galois group of the complex acting on plus minus 1 was isomorphic to z mod 2z, which is in fact isomorphic to the reals modulo the reals squared, right? The reals modulo squares is either just plus or minus 1, which is z mod 2z. All right, great. Let's actually also go back to one of the examples that was the motivation for this. We were trying to fix one exact sequence. So here's another application. We wanted to fix the following exact sequence that went from 1, the exact sequence that came from a squaring, right? So let's start from the actual exact sequence we started from. We started from the same one, but with the complex numbers. The z goes to the squares over the complex numbers. That is exact. And it is of Galois modules of the complex over the reals. So take cohomology. If I take homology, then I'm going to get 1 goes to H naught of G. G is the Galois group of the complex over the reals. G into plus minus 1 to H naught of G. C cross to H naught of G, C cross, and then the delta connecting to H1, G of plus minus 1, going to H1 of G of C cross, and going into H1 of G C cross. Okay, so now this is the invariance on plus minus 1. G acts trivially, so this is just plus minus 1. Here, the invariance will be R cross. Here, the invariants are R cross. H1 of the Galois group of the complex over R going into plus minus 1, we just said that this is actually isomorphic to z mod 2, and it is in fact isomorphic to R cross modulo R cross squared. We also proved ourselves, we proved by hand that this is 0, and therefore this is 0, and it also follows from Theorem 90. Okay, but by that, actually, we did ourselves by hand. So what we get is a fixed exact sequence, thanks to cohomology, that goes like this. So the squaring is not exact, but the co-kernel of that map is the reals modulo squares. Okay, and that makes it the whole thing into an exact sequence, thanks to cohomology. Okay, so this is the exact sequence we were looking for from the beginning. Is that great? Very good. Let's look at some other example coming from elliptic curves. That is going to, if you've been following the graduate course on elliptic curves up to this point, then there is a map here that is going to be familiar. So let E over K be an elliptic curve. And let's assume we've increased the field of definition, so the M torsion is defined over K. So let's assume that the M torsion is defined over K. Okay. Then there is an exact sequence that goes from E to E. I'm going to multiply by M. The kernel is therefore the M torsion. So that is the kernel, so that map is injective. And it is surjective because that's a morphism. It's non-constant, therefore surjective. Okay, multiplication by M map is surjective. Remember that here E means E over K bar. So yes, over K bar, that's surjective. But now, so let me write that here. E really means all the K bar points. Okay, so let's take cohomology and see what happens. Now, I take, first of all, cohomology, meaning with G being the Galois group, the absolute Galois group. Then the G invariance of the M torsion is the M torsion itself because it's defined over K. So what I get is M torsion. The G invariance of EK bar is EK, is the points defined over K because of Galois theory. The points that are fixed by the entire Galois group are those defined over K. Again, E over K. And then I get my connecting homomorphism delta, and it takes me into the H1s, H1 on EM, and then H1 on E, and H1 on E. Okay. And by the way, the action on EM is trivial, so this H1 is HOMS. This H1 is actually just isomorphic to the HOMS. But remember that here G is profinite, so it's continuous homomorphism. So this is isomorphic to the continuous homomorphisms from the absolute Galois group to EM. Very good. So the question is, what is delta in this case? How do we define delta? Remember how we define delta. We let P be an EG, which in this case is just points defined over K. And we pick a Q such that through beta, which in this case is multiplication by M, a Q such that M times Q is P. So an element of K bar on E such that M times Q is P. Okay. And then delta of P is the cocycle that goes from the absolute Galois group to EM, which is given by sigma maps to sigma Q minus Q. And now this should be familiar because that is the definition of the Kummer pairing that we defined at some point. When we defined the Kummer pairing, we were proving the property of the Kummer pairing. We saw that it looked, I said, like, if you see this, it looks like cohomology, and that is why. So the delta P is the map that you get through the Kummer pairing with P evaluated at a sigma, is the Kummer pairing. Okay, so that's how the Kummer pairing arises in cohomology. Is actually the Kummer pairing is the delta that connects H naught of P with H1 of H naught of N with H1 of P. Okay, so that is called also in general, that delta is called the Kummer map. All right, we're almost done. Let me just talk one more section, which is called the restriction, one more property, the restriction inflation. Oops. Let's talk about restriction and inflation. So what is this about? So this is about subgroups of G. So suppose that G is a subgroup, then we actually have a map from H1 to H1 of H by simply restriction. Take the class of a cocycle, and I can map it to the cocycle is a map from G to M, so I can restrict it to H, and I get a map that it will also have the property of twisted homomorphism, and it will be a cocycle on the other side. So this restricted to H, that is another cocycle, and that is called the restriction map. Okay, so is usually just written res. Okay, now if H is normal in G, then we actually have another map, because then the invariants of M under H have naturally a structure of a G mod H module. Now, G mod H is a group because H is normal, and the invariants of M under H have a structure of G mod H module. How is that possible? So let's take a coset in G mod H. How does it act? I just define it to be sigma acting on M, because that it doesn't matter what element of H I'm multiplying by, because if I have something like sigma H instead acting on M, another element sigma H would be another representative of the coset sigma capital H. That would be sigma acting on H acting on M, but H acts trivially, so this is sigma acting on M, so it doesn't matter. So here, what we used is that M is in M, the invariance under H, and little h is in H. Okay, so that is well defined. And then I have another map that is the following. So if I have a class of cocycles in H1 of G mod H, and acting on the invariance of M under H, then notice that there is a map from G to G mod H. I can send G mod H with the cocycle phi into M invariance under H, and that is contained in M. So I can extend phi to a map from G to M in this way. So it gives me that then phi can be considered as an H1, as a cocycle from G to M as well. Okay, and then what I get is a map from H1 of G mod H into the H1s of G to M, and this one is called inflation because we sort of made it bigger, inflated the cocycle, and is called inf in general. And it turns out that there is an exact sequence. There is always an exact sequence relating these maps. So H1 of G mod H acting on H invariance of M goes through inflation into H1 of G acting on M, and then I can do restriction and into H acting on M, and this is an exact sequence. Okay, so the way we're going to use this is in the case of Galois homology. This is very useful because in the case of Galois homology, if we have, for example, G is the Galois group of the absolute Galois group of a field K, and L over K is finite, then H, which is the Galois group of K bar over L, is a subgroup of G. So we can talk about the restriction sequence in cohomology. And if L over K is Galois, then it turns out that H is normal in G, and the quotient of G mod H, so the quotient of the absolute Galois group of K modulo the Galois group of K over L, is actually naturally isomorphic to the Galois group of L over K. Therefore, there is an exact sequence that goes as follows from H1 of the Galois group of the quotient, which is the Galois group of L over K, and invariants that are fixed by L, by the Galois group of K bar over L. So basically elements that are in L of M. Through the inflation sequence, I can go to H1 of the absolute Galois group of K into M, and through the restriction sequence, I can go into H1 of the Galois group of K bar over L into M. Okay, so through theorems like Hilbert theorems 90, I can compute typically things like this. And if I'm able to compute this, then that tells me information about cohomology groups of finite extensions. So this is how this exact sequence will be used in the future. Okay, so I think that is enough for now for cohomology, and I hope this is useful. Bye-bye.